Let's take a look at an electric field due to a charged rod and see how we can do this both as an integral and as approximating that integral as a summation of very many point charges. So here's our problem. We have a rod that is 1.5 meters long and has a total charge of 2 microcoulombs, and we want to calculate the electric field due to this rod over at point P, which is 0.2 meters away from the end of the rod. So we're going to start this out as a regular integral problem. So we know that the differential element of the electric field, dE, is equal to K little charge element dQ divided by R squared, where dQ is simply the linear charge density of the line times a little element of distance, dx. And of course, linear charge density is just the total charge divided by the total length, which comes out to 4/3 microcoulombs per meter. Next, I want to think about the direction of the electric field and assign my axes. So I'm going to set my origin over at the left end of the rod here. Positive x points to the right, positive y points up. I know my electric field at point P is going to point straight to the right. That's very convenient. It means I'm not going to have x and y components separately, that the entire electric field will be pointing in the x direction. So right away I can say that at point P, the y component of the electric field equals 0, and the x component will be just integrating the entire dE term, k dq over r squared. So we can step through that. dq is lambda dx, so we plug that in. Next, I'm going to set my integral limits. I need to integrate over the entire length of my charged object. So integrating from x equals 0, the left end of the rod, out to x equals 1.5, the right end of the rod. And my distance r, it will be 1.7 meters if I'm all the way at the left end of my rod. And as I move along the rod at distance x, it will be 1.7 meters minus x. So quick check, when I plug in my lower integral limit, I get an r value of 1.7. That makes sense for the left end of the rod. If I plug in my upper integral limit, I get 1.7 minus 1.5, or 0.2. That's the correct distance for the right end of the rod. So everything looks good. I'm ready to integrate. That's a pretty simple integral to do. I just get 1 over 1.7 minus x. I need to evaluate that at my integral limits, which I plug in my known value for Coulomb's constant k and our linear charge density lambda, and I come up with 52,941 newtons per coulomb. So that's how we do this problem as a regular pencil and paper integral. But now I want to think about how we could do this numerically to emphasize the idea that an integral is just adding up a whole bunch of tiny contributions. So I'm going to imagine replacing our charged rod here by some number of individual point charges spread out over the length of that rod. So here to start, I'm imagining 10 point charges spread over the length of this rod, and I'm going to set up this calculation in Excel because I don't want to do 10 calculations by hand. So let's jump over to Excel. So here I have the total charge of the rod, 2 microcoulombs, the total length of the rod, 1.5 meters, and I'm going to think about how this looks if I replace the rod with 10 point charges. So I have 10 point charges. I want those 10 charges to add up to the total charge of the rod. So the charge of an individual point charge, type my equal sign, so Excel knows I'm entering an equation, will be the total charge on the rod divided by the number of point charge we're talking about. So 2 times 10 to the negative 7 coulombs. And now I want to think about the spacing between the point charges. I want them to span the first charge to be at the left end of the rod and the 10th charge to be at the right end of the rod, which means I'm essentially taking 9 steps to get from the left end to the right end of my rod, which means that the distance between my point charges will be the length of my rod divided by not 10, but 10 minus 1. Again, that's because the first charge is all the way at the left end of the rod, so I essentially use up the first charge being at position 0. So there's my spacing between charges. Now let's go ahead and calculate what's going on for each of these individual charges. Well, each charge here has a charge of 2 times 10 to the negative 7. I'm going to drag this equation down, and when I drag it down, I don't want to update row 5. So the $sign in front of the 5 there is going to say, as I pull this down, keep filling in this value. So I've got 10 charges. All of them are 2 times 10 to the negative 7 coulombs. What is the position of each of my charges? Well, the first charge starts at the left end of the rod at a position of 0. My next charge will be that location plus my distance between charges. And again here, I'm about to drag this down, and I want to keep adding cell B6, so I'm going to put a little $sign in front of the 6 there. Go ahead and drag that down. So it looks good. The first charge is at 0, the left end of the rod. The 10th charge is at 1.5, the right end of the rod. How far is each of these charges from our point P of interest? Well, we figured that out when we were thinking about the integral. That's just 1.7 minus x. So my first charge is 1.7 meters away from point P. My last charge is 0.2 meters away from point P. Now I'm ready to calculate the electric field. If point P weren't along the axis of the rod, if it were some point above or below the rod, I would probably have both x and y components. So I went ahead and wrote out 2 columns here. But for our problem, we sort of convinced ourselves from the diagram that there is no y component of the electric field. However, if P, again, were a little bit above or below the rod, we would need to do some SOHCAHTOA, and there would be both x and y components for the electric field. So I'm ready to calculate the x component. And here, all we're dealing with is point charges. I just need to calculate the electric field of a point charge and then add up those 10 electric fields. So there's no charge density lambda here, no integral. What we're trying to see is that that integral gives us the same result as adding up very many little point charges. So all I need to do to calculate the electric field is kq over r squared. Well, k is 9 times 10 to the 9, 9e to the 9, times my little charge, q, divided by r squared. So 622.8374 newtons per coulomb is the electric field at point P due to this one point charge. Let's calculate that for each of the individual point charges. So here each time we're updating the distance away. Each point charge is a different distance. And then the integral should just be representing the sum, adding up all of these little contributions. So here in my total category, I'm just summing up these 10 contributions. And I get 76,074 newtons per coulomb. Well, that's sort of in the ballpark, but it's not great. We found, doing the integral by hand, that we should get 52,941 newtons per coulomb. So let me go back and find a percent error here. So my calculated value, 52,941 minus my expected value over 52,941. And let me go ahead and multiply that by 100, just so it does show up as a percent. It's about 43% error, which is not great. But 10 charges isn't a great approximation of a continuous rod made up of billions and billions of atoms. So what if instead of 10 charges, I break this rod into 100 charges? So let me scroll back to the top. So again, I have the same starting point, but now I'm going to break it into 100 pieces. So I need to divide the total charge by 100 now. My distance between charges is now 1.5 meters divided by 99. And here I've already used the same equations and dragged each of these columns down to fill in everything, but it's the same equations as before. And now I get 54,749.57 newtons per coulomb. Only a little more than a 3% error from what we got from the integral. And just for kicks, I'm going to go one better and see what if we break this rod into 1,000 point charges. Well, then there's a whole bunch of dragging down to do. And once I get down to the bottom here, right, this is why we use Excel, so I just have to drag the columns down. I don't have to keep punching things into my calculator or writing things on my paper and pencil. So breaking that one rod into 1,000 point charges, we get 53,116.91 newtons per coulomb, about 0.3% error. So my goal here was to show that the integral really is equivalent to adding up a whole bunch of tiny contributions. And what we see is if I represent that rod by a finite number of point charges, I start getting pretty good results just calculating each of those point charges contribution and adding them up. And if I get more and more point charges, I get more and more accurate results.